Why does quantum theory calculate many possible alternatives when an experiment records one definite result?
Mm,
I mean, think about that for a second. We set up our lasers, we arrange our lenses, we look at a highly sensitive detector, and we see one single registered event.
right, a definite click.
Exactly, a
Yeah.
localized physical mark on a screen.
Mhm.
Yet the foundational math that predicts that single click tells us the outcome actually depends on a multitude of contributing quantum amplitudes, like all these different possible alternatives that we cannot actually see as classical distinct histories. We somehow pull one definite reality out of a calculation of many, many possibilities.
And that tension right there, that is the absolute core puzzle of quantum electrodynamics, commonly shortened to QED.
Yeah.
It is the quantum field theory of electromagnetic interaction. And our focus today is strictly on that profound conceptual tension, the multiplicity in the calculation versus the definiteness of the recorded outcome.
Right.
We are going to dive straight into the physics and the evidence, completely avoiding any biographical scene setting or, historical fluff about Richard Feynman's personal life.
Exactly. I want to jump right into how this actually works. So to wrap our heads around this without getting lost, we're going to follow a very specific roadmap for this deep dive.
Good idea.
We will begin with reflection from ordinary glass. Then we will explain Feynman's arrow-based representation of probability amplitudes. From there, we will show exactly how those alternatives interfere.
Mm-hmm.
And once we have those rules down, we'll connect those rules to electrons, photons, and Feynman diagrams. Then we will examine renormalization, look at the precision evidence, outline the theory's limitations, and finally clarify what QED does not actually settle.
It's a highly logical progression. I mean, it takes us from the everyday mysteries of light bouncing off a window straight down into the mathematical architecture of the standard model.
Right. And the mission of this specific deep dive is to distill the principal ideas of this foundational theory. We want to firmly separate the established, tested facts from the philosophical interpretations. I want to give you, the listener, a clear view of how nature's accounting system actually works.
To do that, we begin with that first step on the roadmap, ordinary glass.
Yeah, just a normal window pane.
Exactly. If you look at a window pane, most of the light passes straight through, but a fraction of it reflects back at you, allowing you to see your own reflection.
Right.
Classical optics explains this using boundary conditions, essentially looking at the electric and magnetic fields and the differences in how light travels through air versus glass.
Right, but the quantum account is completely different.
Yeah.
I mean, it doesn't just tweak those classical rules. It rebuilds the phenomenon from the ground up by assigning amplitudes to different alternatives.
Yes.
For example, there's the alternative that the light reflects from the front surface of the glass, and another alternative that it travels through the glass and reflects off the back surface. And to explain how we calculate this without, demanding a blackboard full of advanced calculus, Feynman used arrows.
Yes, but we must be very precise about what those arrows actually are.
Right.
The arrow representation is a theoretical structure. These arrows encode complex mathematical quantities.
Okay.
So an arrow has a length, which represents the magnitude of the amplitude, and it also has a direction, which carries the phase information. You can imagine that as a process evolves in time and space, that phase changes, meaning the direction the arrow points is constantly rotating.
Like the hand of a very fast stopwatch.
Exactly, a spinning stopwatch hand.
Okay, let's unpack this. How do we actually use these spinning arrows to figure out what a photon is going to do?
Well, it relies on a critical sequence of operations. When you have indistinguishable alternatives, meaning there is no physical record left behind anywhere in the universe telling us whether the light reflected from the front or the back of the glass. In that case, you must add the amplitudes.
Okay.
Visually, you take those arrows and connect them head to tail. Then, and only then, you convert that final combined arrow into a probability by squaring its length.
Wait, squaring its length. Okay, got it.
Yes. But, however, if a process happens in successive stages, for example, a photon is emitted, then it propagates through space, then it hits a detector, in that case you multiply the relevant amplitudes for those stages.
Okay, I have to stop you there because in everyday life, adding more options usually increases the likelihood of an outcome.
Right, right.
Like if I have 5 different routes to drive to a destination, my chances of arriving are pretty high.
Yeah.
But with these quantum arrows, how can adding another alternative route actually lower the probability?
It sounds completely backwards, doesn't it?
Yeah.
But it's because the arrows have direction. They have relative phase. This is where interference happens.
Okay.
So imagine taking 2 arrows and connecting them head to tail. If they happen to point in exactly opposite directions, the second arrow walks you right back to your starting point. Oh.
They cancel each other out entirely. That shrinks your final combined arrow to zero, meaning zero probability.
Right.
On the other hand, if they point in the same direction, they align and reinforce each other, creating a very high probability.
Oh, wow. That makes so much sense. It's exactly like noise-canceling headphones.
Yes.
The headphones listen to the background engine noise of an airplane, and they generate a second sound wave that is the exact opposite phase.
Exactly.
You are literally adding more sound to the environment, but because the phases are perfectly opposed, they cancel each other out and you get silence. Adding an alternative creates a zero result.
That is a phenomenal analogy, yes. You are adding an amplitude that is perfectly out of phase. And that observed evidence is all around us, not just in audio, but in light.
Like the shifting colors on a soap bubble or an oil slick in a parking lot.
Precisely. Those thin film colors are the perfect observed evidence of this mechanism.
Light reflecting from the front surface of that incredibly thin layer of soap travels a slightly shorter distance than light reflecting from the back surface.
Because it doesn't have to go all the way through the film.
Exactly, because the distances are different. The stopwatch hands of their phases have turned by different amounts. Depending on the exact thickness of the soap film and the angle you view it from, the arrows for some wavelengths will reinforce.
Right, giving you a brilliant, bright band of green or pink.
Right, while the arrows for other colors will cancel out entirely. And we also see this observed evidence in diffraction when light passes through tiny apertures. And remarkably, even in experiments where detectors register photons just one at a time.
Oh, wait, really?
Yes, building up an interference pattern click by individual click.
But knowing that light acts this bizarrely makes you wonder, if all these wild paths are canceling and reinforcing, how do we ever get the rigid, dependable rules of classical optics? Like, why does a laser beam seem to travel in a perfectly straight line or reflect at perfectly equal angles in a mirror?
Well, what's fascinating here is how the classical path emerges organically from the quantum math through what we call stationary phase.
Stationary phase, okay.
If you mathematically calculate the amplitudes for highly irregular, chaotic routes that are far away from the classical path, their distances vary wildly.
Yeah.
That means their phases vary rapidly. Their arrows point in every random direction, and when you add them up head to tail, they just curl up into a tight little circle, canceling each other out completely.
So they just eliminate themselves?
Pretty much.
Huh.
But near the classical path, which is the region of stationary phase, the distances of all the neighboring possible routes are almost identical.
So their stopwatch hands are all pointing in almost the exact same direction.
Exactly. Because they point in roughly the same direction, they reinforce each other to create a massive final arrow.
Wow.
The classical straight line path isn't the only route the math considers. It is simply the region where the amplitudes survive cancellation in the short wavelength limit.
That is wild. But, because these quantum rules completely defy our primate brains, they have bred a ton of popular science myths.
Oh, absolutely.
When people hear many possible paths, their imaginations run wild. So before we move deeper, we need to correct some of this magic. Let's talk about some of the most common misunderstandings, starting with the every path myth.
Let's do it.
I have to admit, when I first read about this, I pictured a single photon literally flying out of a lamp, taking a detour around Jupiter, and then flying back to hit my book.
Yeah, that is a severe and very common misunderstanding. Every possible path is a mathematical history contributing to an amplitude calculation.
Okay.
It absolutely does not mean that a photon is physically observed, tracing every classical route through real space. It is a mathematical structure we use to compute the final probability. It is not a physical track you could ever catch the photon driving on.
Which naturally leads to the second major myth, what I call the conscious photon. Because if light is figuring out this stationary phase and exploring all these mathematical alternatives, it makes it sound like the photon knows where to go, or that it's sniffing out the most efficient route.
That implies agency, and photons do not consciously choose or inspect paths. They have no awareness.
Right.
What is actually happening is that the experimental apparatus prepares the state, the physical optical elements transform the amplitudes, and our detectors register outcomes strictly based on the probabilities calculated by the theory. There is no decision being made by the particle.
And what about the big one, the observer effect? If you spend 5 minutes on the internet, you'll see claims that human consciousness collapses the wave function, or that reality doesn't exist until a human mind looks at it.
Oh, yes. In quantum mechanics, observation strictly means physical interaction.
Okay.
It means a detector, a polarization tag, or the surrounding environment creates a physical record that distinguishes the alternative.
So it's not a person staring at it.
No, absolutely not. Remember our glass example. If a physical process leaves a record of whether the photon hit the front or the back of the glass, that physical entanglement destroys the interference pattern. It has absolutely nothing to do with human consciousness, mystical awareness, or a mind creating reality. A rock or a purely mechanical sensor acts as an observer just as effectively as a human.
That's a huge distinction. And lastly, if you're listening to this and your head is spinning with quantum uncertainty, it's easy to fall into the anything is possible myth.
Hmm.
People think quantum uncertainty means every imaginable bizarre event is equally possible, or that it permits faster than light communication because everything is mysteriously connected.
Firmly false. The uncertainty principle is a highly precise mathematical relation between distributions for specific pairs of observables. It is not a license for chaos.
Yeah.
QED predicts highly disciplined, extremely narrow quantitative outcomes based strictly on conservation laws.
So you can't just break the rules.
No, many processes are entirely physically forbidden. Furthermore, relativistic QED is explicitly constructed so that no controllable signals propagate outside the causal light cone. Faster than light communication is simply not permitted by this theory.
Okay, with the sci-fi myths cleared away, let's transition to what happens when this light actually crashes into matter. We've talked deeply about photons, but QED is quantum electrodynamics. It's also about electrons.
Yes, the core fundamental coupling in QED is between charged matter, which is described mathematically by a field like the electron, and the electromagnetic field, which we associate with photons.
And this is where we have to talk about Feynman diagrams.
Ah,
The
yes.
basic interaction vertex in these diagrams is usually drawn as an electron line coming in,
Yeah.
a wavy photon line meeting it, and another segment of the electron line going out.
That basic vertex represents a contribution where the charged matter couples to the electromagnetic field. In plain terms, it allows for emission of a photon, absorption of a photon, or scattering. And just as importantly, because this is a relativistic theory, it includes antiparticles. So you also have positrons, which have the exact same mass as an electron, but the opposite electrical charge.
No, wait a minute. I want to jump in with a crucial clarification here based on our myth-busting rules.
Okay.
Sometimes antiparticles are represented in these Feynman diagrams as lines moving backward in time. Again, the sci-fi alarms are ringing in my head. That doesn't mean time travel is actually happening, right?
Yeah.
And the diagrams themselves, they aren't microscopic photographs of things colliding.
Correct, on both counts. Drawing an antiparticle line pointing backward in time is an incredibly powerful computational convention. It simplifies the math, but it is not evidence of usable messages traveling into the past.
Good to know.
And the Feynman diagrams themselves are mathematical bookkeeping tools. They help physicists organize incredibly complex equations. They are not literal timelines, nor are they photographs of microscopic space. You cannot read them like a comic strip of tiny billiard balls crashing into each other.
What about the term virtual photons? You
Yeah.
constantly hear that charged particles, like two electrons pushing each other apart, exert that force by exchanging virtual photons, like they're throwing tiny energy balls back and forth.
Right.
Are they more like the internal gears of a clock, like stuff we can't see but that makes the visible hands move?
That is a much safer metaphor, yes. The language of throwing energy balls can be useful shorthand, but it is dangerously misleading if taken literally.
Okay.
Virtual photons are not ordinary detectable particles that are somehow magically borrowing energy and violating the laws of physics. They are internal mathematical elements of the calculation.
So just math.
Right, they are part of what we call the propagator structure inside the amplitude. The key takeaway is that energy and momentum conservation at these interaction points is never suspended in these calculations.
Here's where it gets really interesting, because while drawing one basic vertex of an electron spitting out a photon is simple bookkeeping, nature is incredibly complex. An electron doesn't just sit there.
No.
What happens when you calculate higher-order quantum corrections, like diagrams with closed loops, where an electron emits a virtual photon and then reabsorbs it all by itself before interacting with anything else?
Well, this raises a massive historical crisis in physics. When early physicists tried to calculate the amplitudes for those closed loops, they had to account for the electron interacting with its own field at infinitely close distances.
Okay.
When they ran the equations, the integrals completely blew up. They yielded infinite expressions for physically meaningful quantities, like the mass and the charge of the electron.
Which obviously breaks the theory. You can't have an equation that spits out infinity and compare it to a finite real-world measurement from a laboratory scale. It makes the map totally useless. So how did they solve this infinity crisis?
They solved it through a theoretical structure called renormalization.
Okay, I need an analogy here. Is renormalization kind of like calculating your taxes?
Taxes. How so?
Let's say your business makes $1 million in gross revenue, but you have all these messy, endlessly complicated internal expenses and deductions.
Right.
If you just look at the raw incoming cash, your tax bill would be impossible, maybe infinitely high for a small margin business. But once you reconcile the internal accounting against reality, you end up with a finite, manageable net profit that matches your actual bank account.
That is actually a very grounded way to think about it. Renormalization systematically relates the bare parameters in the intermediate math, which are full of those infinite, messy internal
The
self-interactions.
expenses, essentially.
Right, it relates those to the actual quantities we define through physical measurement. You introduce a mathematical regulator to control the infinities, essentially putting a temporary cap on them.
Okay.
Then you combine the terms according to the theory's underlying symmetries and reorganize the math. The final result is that the predictions become finite. They no longer depend on that temporary regulator, and they perfectly match reality.
That is a staggering mathematical achievement. It's like fixing the engine of a car while it's driving at light speed.
It is, and because it was such a monumental task, it requires us to insist on historical precision and share the communal credit.
Right. It wasn't just Feynman.
Exactly. Richard Feynman provided the highly effective diagrammatic contribution, which made calculating these things much easier, but the renormalized theory was rescued and built by Shinichiro Tominaga, Julian Schwinger, and Freeman Dyson,
Wow.
alongside a vast community of experimental physicists who tested every step. The Nobel Prize was shared by Tominaga, Schwinger, and Feynman for this exact reason.
So they mathematically tamed the infinities. But to prove it wasn't just a clever accounting trick, they had to test it against the real universe. Let's look at the evidence, and let's categorize it carefully, because we can't just lump all physics into one bucket.
Exactly. We strictly separate the evidence levels to be intellectually honest. First, we have observed evidence.
Like things we can measure.
Yes. This includes concrete, replicated physical measurements. A famous example is the Lamb shift, a tiny energy difference in hydrogen atoms that earlier, simpler theories completely missed.
Okay.
It was directly observed in the lab, and it perfectly matched QED's calculations of those messy loop corrections. We also observe atomic spectroscopy, incredibly precise magnetic moments like the electron's G2 anomaly, scattering rates, pair production, and even light-by-light scattering at high-energy colliders.
So those are the undeniable physical facts. And we contrast that observed evidence with the theoretical structures.
Yes. The theoretical structures are the mathematical machinery generating the predictions. This category includes the complex amplitudes, the quantum fields, gauge symmetry, propagators, path integrals, and renormalization itself. We don't see renormalization in a telescope. It is the theoretical structure that makes the prediction possible.
Right. But QED doesn't just exist in isolated, perfectly controlled lab vacuums. Physicists apply it to incredibly complex situations, like trying to understand the extreme environment of a neutron star.
Which brings us to our third category, model-dependent conclusions. When you apply QED to strong field regimes, complex bound states, dense materials, or astrophysical settings like black holes or synchrotron radiation in a pulsar, your conclusions are model-dependent.
Because there's so much going on.
Exactly.
Yeah.
The fundamental laws of QED hold perfectly true, but your final predictions heavily depend on the assumptions you make about the environment.
Like the geometry, the background plasma, the approximations.
Right. It is vital to separate the pure, perfectly tested QED interaction from the complexities of the environmental model you've built.
Okay, so if QED is arguably the most accurate theory in the history of physics, predicting things like the electron's magnetic moment to astonishing decimal places, does that mean it solves everything? Does it finally explain the absolute nature of reality?
If we connect this to the bigger picture, the answer is no, and this is where we must highlight what QED does not settle. Certain claims are strictly Interpretive.
Interpretive, meaning we don't have hard proof one way or the other.
Yes. QED calculates probabilities beautifully, but it does not experimentally settle whether all those mathematical paths are physically real in some deeper sense. It does not settle the true ontology of the wave function, what it is in reality, and it does not explain the ultimate origin of how definite outcomes suddenly arise from a superposition of possibilities.
It gives us the how much and the how likely to an incredible degree of accuracy, but it leaves the philosophical what is reality question totally open to debate.
Precisely. And furthermore, in terms of fundamental physics, QED is just one sector. It is not a theory of every force. It does not explain the strong nuclear force that holds atoms together. It relies on the electroweak framework for broader context, and it absolutely does not resolve the massive problem of quantum gravity.
So what does this all mean? We have gone from the simple reflection of light in a window pane to drawing spinning arrows all the way to the absolute limits of the standard model.
It means that QED is an extraordinarily successful theory of electromagnetic interaction. It is a masterpiece of predictive precision that completely relies on the interference of amplitudes.
Right.
But it requires deep scientific humility. It is not an all-encompassing theory of every force, nor does it resolve all interpretations of measurement. It is a highly disciplined framework that replaces classical certainty with a mathematically precise rule for calculating possibilities.
It shows us that nature's accounting system is breathtakingly coherent, even when the rules of that system completely defy our classical intuition. As we wrap up our discussion today, I want to clearly state that this program is an independent Cosmora HQ book overview in audio podcast form, not an official, complete authorized or unabridged audiobook. We strongly encourage listeners to obtain the published work through a lawful bookseller, library, publisher, or authorized digital or audio service. Please subscribe, comment, and share this deep dive if you enjoyed it.
If nature gives us one recorded event, what should we believe the unobserved quantum alternatives represent?